Hello. Hello. Oh, okay. The final project is published on the Moodle, so you can look over the question and let me know if any concern. And it's due December 7th on Wednesday. So you have 3 weeks, 3.5 weeks to work on it. If you include the Thanksgiving, if you include the Thanksgiving, you still have 2.5 weeks to work on that. So you're familiar with most of the part for the project. Only but I also ask you to find a report on some data science website and to criticize their report, because we need to learn from others and also transform those new knowledge to our own. Okay, and also I combined the lesson from this week and ask you all to deploy the project, so you can maybe next year when you have the computer day or some showcase in the department, you can probably use this project. Today's lesson is more of a discussion. We will review some common problems that I found in our data report on the data reports from the website. And on Wednesday, we'll talk about deploying the model. But the slides are instruction already there. You can go with that, and I just needed to research some details and to this and add those to the slides. Okay, so today's lesson is more of a discussion, okay, not just me talking and demonstrating. So the first question I want to ask is, what types of problems are good to use a prediction model? And I listed out 2 examples. One is the prediction goal is to find out people's opinion about a candidate. And give me a second. Okay, I think there's some problem with the video on. Hello? Okay. There was audio. Okay, good. The second example, project, the goal is people vote on a candidate or for a party. So do you think both are good to use a prediction model? No. Yeah. So the second one is a good problem for prediction. However, the first one, when we want to find out people's opinions, we use the surveys to find out. But the people's opinion, these are not outcomes. These are not events. So it's really not that predictable with the historical data. So instead of using prediction model, we don't do that. Some historical data is like, hey, they voted or not, they voted the party or not, or they buy the Starbucks or not. But those are historical data you have. But people's opinion, these are not historical data. Okay? So we predict outcomes and events. We don't predict people's opinion. For example, if you're working for Starbucks, okay, you survey whether you like students at EWG like the product or not, but you can predict use the some data from the database or from the previous data. You can predict whether the student is a loyal member or not, or they bought the Starbucks product or not. Yeah. So it's a slight difference, but really 2 different questions. Second question, numerical variable and the categorical variable, we often get confused. The first one is years, the second one is ratings. This is a feature you oftentimes numerical or categorical years. Yes. Numerical, yes. Most of the times, years are numerical, like the housing. It was built on 1980 or 1970. Usually, it's numerical, and it ranges from it could range from 1970 to 2001. So when it ranges has a range over 20 or 30, it's usually numerical. But if it's just in a small range, like 5 years or less, shorter than 10 years, you can treat it as a categorical to count how many events happened in this year and how many events happened in that year. Then this could be a categorical. And another thing you have to be careful when you use the feature years is, do you care I was born in 1986, or do you care how old I am? Usually in a problem, right? You care about my age, how old I am. When we are considering health, or when we are considering the price of the house. So you need to treat this. You need to transform this feature, okay, to 2022 minus the year, right? So we not care about the year it was born, it was built. We care about how the age. Now, 1986. This doesn't make it's not that useful in this. Ratings. Usually you rate the product from 0 to 5, or 0 even 0 to 10 ratings. These are most of the cases. This is called ordinal data. So ordinal data is a mix of numerical and categorical. But we often treat it as a categorical data. So one standard to divide to judge whether it's categorical or numerical is that if you add the numbers together, would that be useful? So rating restaurants from scale, when you add the 0 to 5 or add 4 to 5, it's not that useful, but it represents the quality of the restaurant, right? So it's most of the time the rating is ordinal, is numerical. No, it's treated as a categorical data. This group of restaurants are good. This group of restaurants, the ratings are low. Okay. Yes. So in a lot of data sets, the categorical data is already labeled with 0, 1, 2, and don't treat them as numerical, okay, features. They are categorical. So the next question is when do we use the box plots? When do we use the scatter plots or grouped bar plots? And sometimes we come to say this is a good box plot. But well, oftentimes you generate some plots and see it's messed up, doesn't look nice, and oftentimes the problem is you didn't use the right plot. Right? Box plots are for categorical variable vs numerical variable, and this y-axis means the range of the data. The scatter plot is used for numerical variable and vs numerical versus the numerical variable to find the correlation, whether those two variables have a correlation. And the grouped bar plot is for categorical versus categorical. Right. So this bar plot looks nice. We often see it. So this is there any problem you see from bar plot? Is there something abnormal? Yes, the second one arranged from 0 to 1. So, and this one is also only has 2 values, 0 and 1. If you see anything abnormal, you probably treated it wrong. Okay, so these actually should be categorical. That is actually categorical, and should be removed. But yes, on some data reports, you see these. I wouldn't recommend that. It wouldn't look not that professional. And of them, so we use the plots, not just I ask you to use plots, or this more make the report more visual. No, we are using the plots to get the information, Okay. If you cannot get any information, if you cannot get any useful information from the plot, most likely you are using the wrong plot. I cannot get any information. Those are all one. No, those are all range from 1 to 0 to 1. And so you need to inspect the result and see if there's anything wrong. Okay, next question. Can I apply correlation coefficient ANOVA or chi-square test for all variables? Any of the tests for all variables? You can, technically you can, and the Python or the Python will still, the libraries will still use the data and give you scores. And we often see people using heat map or using the correlation coefficient metrics for all the data. You often see that in the reports. I don't suggest that. So, for example, correlation coefficient we learned is for what type of data? What type of problem? What is it useful? Correlation coefficient. The correlation coefficient is to examine the scatter plots and see if they are correlated. If they are all the dots are along the line, then the correlation coefficient goes to 1 or -1. And if they are scattered, then it will be low, close to 0. Numerical to numerical data. Yes. For example, so yeah, often for numerical data, and you use a correlation coefficient. Of course, this may close to 1, and if I draw another one, if they are scattered like this, this will still close to 1. Okay. Correlation coefficient is different from the coefficient in the formula y equals ax plus b. It's different. Okay? The coefficient is different, but the correlation coefficient measures whether they have a strong linear relationship or not. It might be close to 1. And this is also close to 1, although the slope is different.
So like for all of that, are the numbers the same as when you do like dataframe.4 and get the correlation matrix? Are those the same numbers you use for making like a scatter plot that way?
Making a scatter plot?
Yeah, like the correlation coefficient. And then you know how we do the correlation matrix with all the numbers?
Yeah.
Are those the same numbers that we use?
Yes. So yeah, either scatter plot or correlation coefficient can reflect whether the dots are close together, whether they have a strong linear relationship or not. Or you can use both, like the ANOVA and the box plot to use.
Okay.
Yeah. So how about how about the scatter plot of this correlation coefficient for categorical data? Can we use it for categorical data and versus numerical data? I will return a number, but that number means something or means something or reliable. For example, here X is a categorical, Y is a numerical. So it could be the data could look like this, right? And if you use a correlation coefficient, of course, the number will be close to 0. It will be low because it doesn't show. However, we learned the box plots and we learned ANOVA. This one does has a influence a significant difference. There's a significant difference between these two groups. So this variable has an influence on I. So I wanted to suggest correlation coefficients for categorical data. Okay. And same with ANOVA and the chi-square test. ANOVA is for analysis of variance of the variance for is used for what type of data we use ANOVA, what type we use a chi-square test. Numerical versus
So you just do it against the
ANOVA.
Right.
ANOVA is for numerical versus no. Numerical versus numerical, we use a correlation coefficient, a scatter plot often. ANOVA is often used for categorical versus numerical, yeah, to see the variance between two groups, between groups. And these two, all these use the different algorithm to calculate the numbers. So ANOVA, when we use ANOVA, there are two groups, 0 and 1, and the y-axis is the numerical, y-axis is numerical, and you could have these two box plots. And the ANOVA test, the result shows the variance. It shows the variance between the groups. The variance between the groups divided by the variance within the groups. So for example, in this case, Yeah, in both cases, the means between different groups are different. However, this one, the variance, we know this one, the data with between these two groups has no significant difference, right? The range almost the same, and for this data, for this case, these two groups have a significant difference. So why? The variance between these two groups, the mean between these two groups, it's almost the same. Same distance, same distance. However, the variance within this group, so the variance within this group, it's big, it's huge, bigger than the variance between these groups. So that's why this one, the F score could be low, and there's no significant difference. And this one, the variance within this group is very small. So then there's a difference between the group compared to the variance within this group. It's significant. So that's when we use the ANOVA to calculate the variance between the group divided by variance group. If it's a categorical data, okay, there's variance also. It's not that useful. Okay. And the chi-square calculates the errors between the groups. This kind of question, how ANOVA is calculated, or how the algorithm works. These are some frequent questions if you go to the interview. Some job, you have to describe how this works, although you may not have to calculate this. Chi-square test is used for. I need to reflect from my memory also. Chi-square test is have two data. So this is could be the zero group. This could be the one group, and this could be A, B, C, and we are seeing in group A, there are like a 20, 30, and if we in group B, there are maybe 10 and 30. Group C, maybe 40, 60. And I'm trying to see, hey, whether there's these difference, whether there are these number, these ratio are different between these groups. So how do they do this? They calculate the total number here and the total number here. So the negative ratio to the positive ratio should be the total, the ratio for the total could be maybe could be 2 to 3, and then they compare this ratio to the ratio here, if there's a difference or not. Then if this ratio, the error for this ratio to the standard ratio to the total ratio, if it's largely different, okay, there's a difference between these groups. So that's how it works. So again, I would apply these method for different type of data, okay, but not to apply them for all the features. Okay. This question. So there are two examples here. I cut out two examples. In this example, we can see this the p-value for the chi-square from the chi-square test. All the p-values are larger than 0.05 almost, except two, probably two. There are two. There are one, two are smaller than 0.05. So, and in this case, different. All the p-values are smaller than 0.05. So it leaves us over 10 features. Now, shall we cut out all the features here? In this case, shall we remove all? Shall we keep all the features?
Like if they give you any sort of insight to the features.
Yes, exactly. So in this case, yeah. So we can keep these two variables, and this was a project to predict whether the person may have a lung cancer or not, and yeah, after I look into the variable, these are a little bit higher than 0.05, but they are actually for the feature whether the person have short of breath or not, and whether the person have coughing or not. These we know are common symptoms of lung problem. Yeah, so in such case, it's better to keep the features, even though the p-value is higher than 0.05. Right? So yeah, in all data projects, you have to examine the result with your knowledge, with your domain knowledge. And then this case, all the values are smaller than p-value. So we keep all the features. We can keep all the features, but it will make the prediction model complicated. And actually, the prediction model, it depends on really the strongest features, the best features. So in this case, I will select maybe 5 out of these features. Yeah, don't keep the features over 10. I would suggest keep the features that fewer than 10 features. It makes the prediction model too complicated. And especially this week we are learning the deployment of the model. And if your model is too complicated, you have to import multiple variables and make the model inefficient. Okay, so yeah, judge the result, make the decision upon your domain knowledge. Domain knowledge. And this is a common problem I see across the report. There are too many features. They often drop the feature and without any explanation. I don't think this feature is relevant. Yeah, you can drop the features sometimes. It's a long term. It's all uniform values. I want to drop it, but whenever you drop any feature, add an explanation to justify the decision. Okay, or your audience may wonder why you take this step. Yeah. So it's always good to add an explanation and add comments when you write the report. So here, in this project, the student did a linear regression model, and he did all the steps correct, I give him 100 point. However, the model returns the R-squared score is very low. Now R-squared score it goes from 0 to 1, and 1 means the testing data what is the R-squared error? What is the R-squared score?
Standard difference. Linear regression.
Yeah, linear regression. This is prediction line. This is predicted line, and then it calculates the distance to the prediction, predicted result, and it divided by the mean of the the variables. Yeah, there are two. One is the sum of a squared arrow. Sum of the squared arrow is all the distance to here, and the other is the R-squared score. It is average, the average. So it measures the whether the linear model is good or not. So it's very low means the linear model is not good. Why it happened? I take all the steps correct. I did all the steps correct. So linear regression model is built on the whether the feature has a strong linear relationship with the target variable or not, right? So if all the features go like this, they really don't have a linear relationship with the target variable, even if you add the features together. It will not give you a good model. So in such case, when you try to use the linear regression model, it's good to use scatter plot or correlation coefficient metric to examine whether the variable have a relationship, a strong relationship with the target variable or not. Yeah, if they don't have a relationship with the target variable, maybe you can consider other algorithms. So it wouldn't be fit for. It wouldn't be fit, and it cannot return a high R-squared score. Okay. So that's okay. The next one is report in my accuracy score. Remember accuracy score and the F1 score. My accuracy score is good. Okay, over 80%. That's pretty good. Nice. But my F1 score is 20%. Okay, I'll just hide it. So it shows my model is good. It's a good model. Is that a correct measure? Should I just abandon the F1 score so we keep the accuracy score so it shows that? So when would this happen? The accuracy score is good, but the F1 score it looks very low. F1 score is F1 score is often used for when their data set is imbalanced. So if we look at this. If we draw a matrix, the confusion matrix, right? And this is the Y testing data. Testing data is probably 0 and 1, and this is the predicted data. predicted. Okay. And this is 0 and 1. This is 0 and 1. Okay. This is 0. Okay. This side is 1. So and I use this A, B, C, D. Accuracy score is how many predicted correct in total. So it's B plus C divided by A, B, C, D. A, B, C, D. Now, what is the F1 score? F1 score is the calculation of two scores. One is the precision, and then one is the recall score. So the recall score is the amount of cancer patient. Now, how many were find out? How many were predicted out? So this recall score is what is the recall score? This is the testing data, right? Yeah, this amount. All these people are actually having cancer, and how many are predicted out? So recall score is B divided by A plus B, and the so the precision score is all these patients were predicted out positive, and how many are actually positive. And so in case those if the score is low, some may be mistreated. So the precision score should be how many were predicted how many were predicted positive, right? And these are all predicted positive. How many are actually are positive? So it's B divided by B plus D. Okay, so the F1 score takes both of these scores. Then when could this happen? That the accuracy score is good, is high, but this this F1 score goes low. When could this happen? So this number is good, and this number is low. When could this happen?
More data in one category.
That's right.
So, like,
That's right. If we look at these two formulas, if B is small, C is big, then this drags the accuracy score up, and this one will be low. So if we do this on this confusion matrix, it could be like this is the 100, and this is the just 10, and these could be maybe 20, okay, 20 or 30 or 20. So so yeah, then in this case this number will be decent good, added together 110. But this number, it goes very low. It goes very low. So yeah, when the testing data has a lot of false negative cases, and the positive cases are a small number, then this will these two schools will be very different. So, one thing you can do is to cut out some of the cases in the testing data, so this will be more balanced. You see the imbalance that when the data is imbalanced, not just really influence the scores. So I suggest we cut out some of the this data and the testing data in the test data. Balance it. Use the under sampling. We don't want to add samples. We need to keep the authenticity of the test cases. So yeah, cut out some of cases in the testing data and then see how this score look like. Or you can explain why this F score is low. Okay, and people will understand. Hey, that will understand that. So people will understand this. And in some cases, they really don't care if it's not lung cancer or patients. In some cases, they don't care about this F1 score. Then it's also fine. But you need to always explain the result. Okay, this concludes our lesson today, and the next on Wednesday we'll have our last lecture to to deploy the project with the Flask framework. Okay, REST API. And if you haven't finished the assignment for this week for the text mining, you can work on it and ask me any question. Yes, yeah, I haven't looked at your email yet.